bottom of the screen. And like, why? It's very distracting. I wonder if somebody could turn it off. There's some option about that because that's going to really annoy me. Okay. Oh, it's WebEx Assistant. I'm going to turn it off. Okay. Now, speaking of recordings, let's make sure it actually is recording. Yes. Okay. So the recording from last time was an absolute disaster. So I will re-record Tuesday's class either tomorrow or Saturday. So I'm just gonna, I have my MATLAB diary from that day. I'm just gonna sit in my office and start a WebEx meeting and just run through it and make sure it's all recorded. If I feel like it's a small amount, that would be one thing, but it's now our 15-minute class and there was only 16 minutes of recording. So that's too much to have lost. So sorry about that. I now know that when I go for a break to not close my computer. That seemed to be the change that led to all the trouble. Okay, so that's one thing. Okay. Homework 2 has been posted, so both places, Canvas. So you'll find the list of problems there, and it's from a section that I'm going to start today. Now, homework 1 is due on Tuesday, and then we're going to have homework due once a week for a while. So, I mean, I spent a ton of time on MATLAB, but I'm only going to spend 1 week on each of the next couple sections. Okay. All right. So now the notes that I have here, notes for September 9th and 14th. So, so all my notes for section 2.1, but I'm going to cover that today and Tuesday. So I'm not going to get through all of it today, but between the 2 days I will. But I'm going to post all of it after class today, and then what you would see posted in Canvas for on Tuesday, it'll be the same notes except it'll be updated with whatever happens on Tuesday. So afterwards, it'd be best to look at that. And if time permits, at the end of the day, we'll see if anyone has homework 1 questions. All right. So what I'm getting into now is chapter 2, error analysis. So the whole chapter is about errors, but this first section is on error analysis in general, and then section 2.2, which will be the following week, will be about specifically Roundup error and computer arithmetic and how all that works. So what we see in this chapter, fundamental concepts that we'll revisit for specific problems for the remainder of the semester. Okay. And so to jump in here about error analysis, I've actually seen this definition of numerical analysis given. That they would define numerical analysis to be the study of errors in computation. And certainly, error is one of the fundamental aspects of numerical analysis, but I wouldn't say it's the entire field. It's a little more readable. Okay. So, because, yeah, we are trying to produce approximate solutions to various problems, and we do want to be able to quantify how accurate they are. We want to have some upper bound, if possible, on how far off the solution can be in comparison to the exact solution. So error analysis is needed for that. But we keep in mind three criteria for a numerical algorithm. It needs to be accurate, it needs to be robust, or I like to use the word reliable, and efficient. So if you focus solely on error analysis and say, okay, that's what numerical analysis is, you're forgetting about the efficiency part. But one thing you have to be careful about, though, is that when you modify an algorithm to make it more efficient, if you're not careful, it could become less accurate or less robust. So that's something to keep in mind. That there are a lot of changes are made to algorithms to improve efficiency, but also, like for instance, perhaps just to stabilize it. Here's an example you might not all be familiar with. If you've taken enough linear algebra, you may have learned about a process called Gram-Schmidt orthogonalization. So the way they teach that in standard linear algebra class is not a good way to implement it numerically. That's called classical Gram-Schmidt, but there's a change called modified Gram-Schmidt. And it's a slight change, but it makes the algorithm much more feasible on a computer, where you have to think about computer arithmetic. So, and something like that would never come up in an ordinary linear algebra class. So, sources of error, all the different sources, play a fundamental role in the design and implementation of algorithms. And the analysis that we perform is mainly about very accuracy, but also these other aspects. Okay, so yeah, it's not everything, but it is extremely important, and that's why a whole chapter is devoted to it here. Okay, so to think about this super abstractly, you can think of any algorithm as evaluating a function. So x is whatever input you have, whatever problem data. And then the solution to that problem, that's y. So the algorithm that produces y from x, that is your function f. In our examples here in this section, I may use very simple examples for f, functions you're used to seeing like from calculus, but function f could be as elaborate as you like. So when you are using a numerical method to try to obtain an approximation to y from whatever input x, there are all kinds of ways in which error can be introduced. So the two main types of error, we have data error and computational error. So data error is any error in x itself. For instance, what if x is obtained by measurement? Measurement inherently is going to be erroneous. And that's something to take into account, that immediately imposes a ceiling on how accurate y can be, because there's already error in what's coming in. So even if function f is evaluated exactly, there's still going to be some error. Everything else falls under computational error. So that's the process of actually evaluating the function f, at least approximately. And there are many sources of that error that will come up throughout the course. So I want to establish some notation. So y is what we want. Y hat is what we get. So instead of computing y equals f of x, what your algorithm will produce is actually y hat is equal to f hat of x. So I'll fill that in here. And also the input cannot be taken for granted. Okay, just because there's some measurement error involved. Maybe so whatever measurements you have, maybe they can't be represented exactly in the number system that your computer is using. So right there's error, and that's data error. But then there's our source of error in getting from here to here. So what are the different types of error we can have? So discretization error So certain continuous quantities are approximated by discrete ones. A simple example is a derivative. So a derivative is defined as a limit of its difference quotient as h goes to 0. So the simplest approximation of a derivative is this one right here, where instead of letting h go to 0, we choose an h, for example, some small value. What we'll find is, you might think, oh, the smaller you choose h, the more accurate your approximate derivative will be. But it turns out that's not entirely true. And one of the things we'll learn about towards the end of the semester are different ways of approximating derivatives using formulas such as this one. And this is just the simplest one. It's called a forward difference when h is positive. Another example, an integral. So you can approximate an integral using a Riemann sum. That's generally not an effective way to approximate an integral, but so anytime you have a quantity that's defined as a limit, then instead of taking the limit, you can take the expression that you're taking the limit of, and use that as an approximation. So that's discretization error. Truncation error. There are processes that can produce the exact solution if they're allowed to work infinitely, like for instance, perform infinitely number of iterations, or maybe an expression is defined as an infinite series, but of course you have to stop sometime. You can't take infinitely many iterations. You can't use out of infinitely many terms in a series. So because you're cutting something off at a certain point, that would be truncation error. We've actually seen an example of this from a MATLAB tutorial, Newton's square root, that performed Newton's method to compute the square root of 2. And the algorithm ran until the difference between iterates was less than 10 to the minus 15. And so it would have actually gone further, but there would have been no point going further, just because it's not possible to represent numbers in a computer using infinitely many decimal places. We're looking for a square root of 2, which is an irrational number. So we had to stop sometime, and so that algorithm, by stopping the loop at a certain point, incurred truncation error. Taylor series is a very good example of truncation error. That you want the exponential. For instance, you could use a Taylor series approximation, but you're going to stop at a certain point. And the nice thing is, with Taylor's theorem, we have what's called a remainder, and we can use that to get an idea of how large the error can be when you cut off after a certain number of terms. And then there's Roundup error, and a whole section devoted to that, because real numbers are represented using limited storage, so there's going to be error incurred from almost all arithmetic operations, and how we deal with that. So these are the different types of computational error that we'll see. Now, so numerical analysis can be challenging because of aspects of the problem you're trying to solve, as well as the algorithm you're using to try to solve it. We want to make sure to at least starting with a problem that is well posed. Now, Hadamard stated conditions for well posedness, and he formulated them for problems involving partial differential equations. But those principles can be applied to more general problems. That a problem is considered well posed if, number one, it has a solution at all. Second, that solution should be unique. And the solution depends continuously on the data, so what I need to interpret that for you, that if a small change in the problem data, in other words, the input x that we have here, should not lead to a large change in y. And unfortunately, there are certain problems like that that are ill-posed. That the tiniest change, I can actually contrive a problem like that now. I actually have done it in the section. you're solving system linear equations, and AX equals B, and you make a very tiny change in B, for instance, and that can potentially lead to an extremely large change in X. So problems like that are very difficult to solve numerically. So if a problem is ill-posed, if you have a situation where small change in data can lead to a large change in the output, then that problem is intractable numerically. My favorite example of that is from rather advanced linear algebra. Is the Jordan canonical form. Because the Jordan canonical form is used to compute, it involves the eigenvalues of a matrix as well as its eigenvectors and generalized eigenvectors. Generalized eigenvectors come about when an eigenvalue repeats. If you have a matrix that has two eigenvalues that are distinct, but extremely close together, that matrix is still diagonalizable. But what if a small change makes those eigenvalues equal? And what if the resulting matrix is not diagonalizable? Then an element of a Jordan form can change from a 0 to a 1 with the tiniest change in the matrix. So in other words, the Jordan canonical form is not a continuous function of a matrix. Is not a continuous function of the entries of the original matrix. Therefore, it's simply not a good idea to try to compute a Jordan form of matrix numerically for that reason. So whenever you're in a situation like that, numerically, don't bother. Right. Most problems, you don't have that issue, but it's important to be aware when that can happen. Okay. Now, what's interesting is that sometimes it is possible to work with ill-posed problems. So I say ill-posed problems generally cannot be solved numerically by any method. But I do want to mention a counterexample of interest. Okay. So an example of this is called the Perona-Malik equation, the PDE, from image processing. It was actually discovered by taking a discrete version of it and then taking the limit to arrive at a continuous PDE. It is ill-posed, but it is possible to solve it numerically. You have to be careful how you do it. Its purpose is denoising of images. It's also useful for sharpening images, so deblurring. But theoretically, the PDE is ill-posed due to a lack of continuous dependence on the data. But numerically, it can be worked with. That was a small part of my research program several years ago. So the concept of a well-posed or ill-posed problem relates to conditioning, which is something that I'll cover a little later in this section. All right. So now I need to define several terms related to error analysis. So now we really get into the nitty-gritty here. So as I mentioned before, y is our exact solution that we're pursuing. Y hat is our approximation. So we have two notions of error. absolute error, relative error. Now, different books define these concepts differently. Some will use the absolute value. I've chosen not to here. Usually, the magnitude of the error is what is of interest, but not always. So here we have approximation minus the exact for the absolute error. And then relative error, same thing, is divided by the exact solution provided that it's non-zero. Now, since we have these two notions of error, which should be used? It depends on the problem. So here are two examples, where here we would be the exact values, and here are approximations to those values. And what you'll see is that in both cases, the absolute error is the same. In both cases, the approximation differs from the exact by 0.1. But if you take a relative error, in this case, you're going to divide by 100. So while the absolute error is 0.1, the relative error is going to be, so 0.1 divided by 100, so 0.001, whereas in this case it's going to be 0.1 divided by 0.5, it's going to be 0.2. Here's another example. Here we have extremely small exact value, and we have a approximation that's also very small, and the absolute error is particularly small. But if you computed a relative error, you would take the small absolute error and multiply and divide it by this, which would make it very large. So a rule of thumb for which error measurement to use. Dang it. I'm going to get these extraneous characters in here. Okay. Is if the exact value is near 0, then it's best to use absolute error. Relative error could be misleading. Otherwise, it's advisable to use relative error.
You say near 0.
Yes.
Sorry, that's kind of relative to okay.
How
a decimal.
It's not meant to be the exact statement, but
yeah, I'm sorry. I just
okay. Let me make this. I can make this slightly more precise. Whoops. Stop it. That's Microsoft Office thing. Like if y is, I don't know if you've seen this notation before.
okay.
Where a double less than sign means much less than 1. Because that's a case where the relative error is going to be extremely large compared to the absolute. Now, if the magnitude of y is around 1, then the error measurements will be about the same. So on the flip side, if y is incredibly large, let's suppose your absolute error is 1,000,000. That sounds awful, incredibly awful. What if your exact value is a googolplex? Then
it's okay.
Yeah, that's actually truly accurate. So I don't know if that answers your question.
Yeah. So much less than 1, I might be dependent upon the situation.
Well,
0.01. I mean, sorry, yeah.
0.01?
0.01.
Okay, 1%. So I would not call that much less than 1.
Okay, you would not call that much.
Yeah.
Okay.
Yeah.
Just curious.
I think it's something like this.
Yeah. I mean, I can see that's much
Yeah.
less than 1. I'm
Okay.
just trying to decipher where the
Yeah.
much less might start. Yeah.
Yeah.
So it might be different situation.
Yeah.
Sorry,
Also, you got to think about your computer arithmetic system. Like the default one, double precision floating point, gives you about 60 decimal places of accuracy, but single precision only gives you 8. So if you have a number that's too small, it will be declared 0. And then sometimes the floating point system needs to be taken into account as to how much accuracy you can reasonably expect. But yeah, I mean, this isn't exact. It's not exact science, but.
Sorry, I was
Okay,
just
okay.
I was just kind of curious maybe
Okay.
where to start thinking about
Yeah,
it. Okay.
I got nothing there.
All right, that's fair enough.
I mean, I have my own personal rule of thumb, but yeah.
Yeah.
Okay. All right, now that I've given you two notions of error, let's throw in more. Forward and backward error. Now, like I mentioned, this is what we want. This is what we get. Although if I would be really picky, there would be an approximation of x also because there can be data error. Now, the error that I've just been talking about, the error in y, that's forward error. Now when it's clearly understood from context, you might just call it the error, but yeah, the error in the output is called forward error. And that's what we want. We have some input data, we're running it through some algorithm, we're going to get some result. How accurate is that result? However, forward error can be difficult to ascertain. And whereas backward error, error in the input, can often be easier to figure out. And we may be able to use that to at least estimate what the forward error is. So backward error analysis relies on a key assumption, an assumption that doesn't always hold, but oftentimes it does. Now what we do is, we make an assumption that the approximate solution is the exact solution of a nearby problem. And that is given in the form of an equation here. So I've represented the approximation as f hat of x. But what we do is instead choose to think of it as f of x hat. So I've moved the hat. What does that mean? That our approximate solution means we've taken some erroneous input. We don't know what the erroneous input is necessarily, but run it through the exact algorithm. And the reason why this is so helpful is now both our exact solution and our approximate solution are represented using the true function f. So our approximate process, or our algorithm f hat, is taken out of the picture. And now we can use derivatives. Like if f, the exact f, is a differentiable function, then we can take derivatives. And that can help us estimate forward error in terms of backward error. So, how can we get backward error? Like if we have an approximation already. Actually, I'll be able to show you some examples, but okay. So suppose we have this is our input. Here's what we're looking for, the exact value. And here's our approximation. So this is the error that we're looking for, at least the absolute error. But we can think of that as f of x naught hat. F of x naught. Right. By our assumption about backward error analysis. Now, this is the absolute backward error. And we can use this equation to solve for x naught hat. So the fact that these are equal. So what I'm going to do here is I'm going to show an example of how it's done from the book. Okay. As soon as I find the right page, I'll change my screen share. sharing, reshare. Okay. So here's the process I was talking about. So here's our exact result, sine x, and here's our input. So you think this is x naught, pi over 4. Now, here's an approximation to sine pi over 4. It's only correct 4 decimal places. So, we can compare this to the true value of sine pi over 4, square root of 2 over 2. And this is the absolute error. Now, what we can do is take our approximation and find what angle gives us this value. So we're solving this equation. Sine is equal to 0.7071, our 4-digit approximation. And this is our x naught hat. So this is an approximation of pi over 4. So that's our x hat. So now we can compare this value to pi over 4. And this is our backward error. So we're backtracking. And it's because we're assuming that the erroneous output is the exact solution of a nearby problem, where this is the nearby problem, the nearby input. Question about that? This is another example of the same thing. So we have, this is our input, this is our true algorithm, we get our approximation. So then what we can do is, since our function is e to the x, if we take the natural log of this, that is the approximate input, x hat, whose exponential gives us this approximation. That enables us to get our backward error. And notice, our exact input was 5. Our erroneous input that produced the approximation is close to 5. So we do have a small backward error. But what we can see here is that if you look at the backward error, it's on the order of 10 to the minus 7. The forward error is significantly larger. It's still small, but 2 orders of magnitude larger, 10 to the minus 5. By contrast, with sine, here's our backward error. It's nearly 10 to the minus 5 in magnitude. This is only slightly smaller. So with sine, forward backward error about the same magnitude, whereas the exponential is not the case. So what does that mean? What is the relationship between forward and backward error? Any questions about either of these? All right. We'll take a break at this point, and then I'll talk about that relationship. I'll come back. Hopefully not mess up the recording. That's pretty. Okay. We're definitely recording again. Okay, now, admittedly, those examples are heavily contrived. But the idea is to illustrate through some concrete examples where it's possible to figure out everything involved. Getting values for x hat and y hat to illustrate the relationship between forward error and backward error. Because what we saw from the example involving sine versus the example involving exponential, just because backward error is small doesn't mean that forward error is going to be comparably small. There can be a difference in magnitude between them. And it's easy to assume that just because your input, if you have some confidence that your input is only going to be off by a little bit. For example, you have an upper bound in your measurement error. That doesn't mean that your output will not be thrown way off. Okay, so that's what these examples illustrate, how to get all the quantities involved, just so you can see, oh, here's a backward error for this example, here's a forward error. So the relationship between them is about conditioning. So what we want to emphasize is the condition is a property of the problem that you are solving, the underlying problem, the exact algorithm F, not the method you're using to solve it. So stability is about the algorithm in question. So problems have conditioning, algorithms have stability. Now, the condition number, as a simple definition, is forward error divided by backward error. Now, I've already mentioned that we have relative error and absolute error. It holds for both cases. So as long as you're consistent, so you can have forward absolute error divided by backward absolute error, and that is absolute condition number. And the same is true for relative. And I'll talk about both of those in a little bit. So usually when people say condition number, they're referring to the relative condition number. But that's something that so as a default. So if you can have an idea as to how much the backward error can be, for example, quantifying measurement error, which is something that is possible in many cases, and if you have a handle on the condition number of a problem you're trying to solve, and for certain specific problems we can obtain that, then that allows you to get an idea as to how large the forward error can be. So this is why backward error analysis is important. Because you want forward error, that's the goal all along. But trying to ascertain forward error directly might not be possible. So this is our end run around that, using backward error and condition number. So how do we estimate the condition number? Okay, so absolute condition number is absolute forward error divided by absolute backward error. But y is f of x. Now y hat normally is f hat of x, but remember, we're making the assumption from backward error analysis that the approximate solution is the exact solution of a nearby problem. So we only have f here, not f hat. But this is a derivative. So this is approximately equal to f prime of x. So for derivative, if assuming the function is differentiable, which is not always true, the derivative gives us an estimate, that is an estimate of the absolute condition number. So, So here's an example involving condition number. Okay. So here's my function. I'll just work with x cubed. Something simple to illustrate the ideas. Here's our true input. And we're going to make an assumption, like this is our measurement error, that our backward error can be in most bits. So we know what our exact output is supposed to be. It's going to be 4 cubed, 64. But knowing its backward error can be this much, how much can the output be thrown off? And we want to estimate that using condition number. Okay. So here's our absolute backward error. And then we divide that by 4, and that's our relative backward error. So now we have both of those. And as I mentioned earlier, the absolute condition number can be estimated by the derivative. Here's a relative condition number. And that comes from, if I were to go through this process, except instead of absolute errors, I have a quotient of relative errors. So this would be divided by y, the numerator, and the denominator would be divided by x. So that leads to x in the numerator and y in the denominator. So this is our estimate of the relative condition number, but again involves a derivative. So now I'll just go ahead and evaluate these two condition numbers for a function that we have and for the x that we have. So here we have our absolute and relative condition numbers. So notice that regardless of x, the relative condition number is 3. And then here I have to plug in x equal 4 to get the absolute condition number. That would be equal to 48. All right, so now we can use these condition numbers to estimate forward error. So in the absolute case, here's our absolute backward error. And then here is our absolute condition number, but we evaluated at 4. And we get 4.8. So notice the input being thrown off by 0.1 at most could throw off the output by a much larger amount. But what about the relative condition number? So that's the relative backward error times the relative condition number. Notice that's much smaller. But still, it's 3 times the relative backward error. So let's see if these estimates are any good. So as an example, I'll let my erroneous input be off as far as possible, so 4.1. So I go ahead and evaluate my function at x hat compared to the true input and true output. So my absolute forward error is 4.9. My estimate forward error, 4.8. So that's fairly close. And then the relative forward error, 0.0769. My estimate was 0.075. Again, pretty close. So at least in this example, by taking backward error and that's known going in due to uncertainty in measurement, for instance, and what we know about the function, getting its condition number, we actually can get a reasonable estimate of how far off the output will be in either an absolute or relative sense. And yeah, this does seem pretty bad, but keep in mind the exact value is 64. So that's something a bit. The fact that we did divide this by 64, then that's exactly what we would get here. We can see that here. So questions about how the backward error and condition number are used to estimate forward error. All right. Now, as I mentioned earlier, conditioning is a property of a problem, stability is a property of the algorithm. So I'll give an example of to appreciate the distinction. Now it's from linear algebra, but using something you would have seen in a using techniques that you would have learned in the first linear algebra course. So suppose you're solving a system of linear equations using Gauss elimination, like row operations that you would perform, for instance, in a class like our Math 326. Now, we'll assume that the matrix is well conditioned, but let's suppose that this entry, the first row, first column, is extremely small, 10 to the minus 10. Now, because this entry is non-zero, then it is possible to solve the system of equations without performing a row interchange, because you must perform a row interchange if you're in danger of dividing by 0. We don't have that here, So you go ahead and leave the first row where it is. But Gauss elimination without pivoting, and this is actually something if you end up taking the second course, Math 461, 561, I cover in detail there. That if you don't perform row interchanges in a situation like this, where this diagonal entry is very small, that is an unstable algorithm. So even though a problem is well conditioned, the answer that you're going to get may still be inaccurate. What you should do instead is use a stable algorithm, Gauss elimination with pivoting, and that has been proven to be numerically stable. So, even though a problem is well conditioned, it's important to keep in mind which algorithm you're using. Just like, for example, I was talking earlier about Gram-Schmidt, classical Gram-Schmidt versus modified Gram-Schmidt. Classical Gram-Schmidt is numerically unstable. So even for a well-conditioned problem of making vectors orthogonal, you still might get an inaccurate result because you're using an unstable method. On the other hand, if your problem is well-conditioned and your algorithm is stable, then you can expect your approximation to be accurate. Now, unfortunately, in a lot of very important problems, you do not get these properties. For example, if you're solving partial differential equations numerically, that results almost always in problems that are ill-conditioned. That's unfortunate. But when the stars line up, then you can trust the answer that is output.
Professor,
Yes.
well conditioned is the same meaning as well posed, right?
Well, conditioning is about the third condition, third criterion for well-postedness.
Oh.
So conditioning is not really a commentary on whether there's an existence of uniqueness, but just about the question of, can a small change in the input potentially produce a large change in the output?
So it will avoid like chaos or something like blowout, you know.
I'm sorry, what?
Yes. You can avoid chaos or something like blowout.
Right, yes. Yeah, for instance, certain differential equations where a solution is known to exhibit a law of infinite time,
Yes.
then yeah, that would not be well posed. Probably the best known example from differential equations is the heat equation solved backward in time. Well, with regard to, one second.
I want to know if the value of the condition number has any interpretation.
Basically, if the larger the condition number, the more ill-conditioned it is. So we want condition numbers preferably to be small. Ideally, like around 1. Well, like for linear systems, the condition number has to be greater than or equal to 1. Now, in the example I had with e to the x, if x is positive, then the condition number will be greater than 1. But if it was e to the minus x, then it would be less than 1. So that can happen. So if the condition number is, I know this is vague, but much greater than 1, then that's the situation we want to avoid. So that means it's terribly conditioned. Now, in the case of matrices, like suppose you have a non-singular matrix, so AX equals B has a unique solution, but let's suppose it's terribly conditioned. The condition number in that setting for linear systems is actually a measure of the distance between your matrix and the nearest singular or non-invertible matrix. So you can think of a singular matrix as having a condition number that's infinite. If you are familiar with singular values, the condition number of a matrix is the largest singular value divided by the smallest. So the matrix is singular, the smallest singular value is 0, so it really would be infinite in that case. But yeah, one of my students in her research was solving like a family of systems of linear equations that controlled by a parameter, and as the parameter increased, the systems got progressively more ill-conditioned until at some point, as far as floating point arithmetic was concerned, they were considered singular. So at that point, the solution was complete garbage. So that was unfortunate.
Excuse me, sir.
Yeah.
Is it somewhat similar to singular vector decomposition?
That's actually what I was referring to, yeah. Or the singular value decomposition that produces singular vectors and singular values. Yeah. Okay. All right, I'm going to leave the remainder of this section, like talk about convergence. I'll leave that for Tuesday. But that means we have time for questions about this or questions about the first homework.
So, Professor, you mentioned that the conditional number of matrix is that maybe the distance between a non-singular matrix to a singular matrix.
Yes.
So how can we measure the distance between them? Use something like Euclidean norm or some?
Yeah, well, a condition number, its definition is dependent on the norm.
Yes.
So you select a norm. So as an example, so if you take the condition number of a matrix in a particular norm, whatever that value is, that means that there's a matrix that is that close in the two-norm sense that is singular. And you can actually construct that matrix by taking the smallest singular value and setting it to 0. And in the singular value decomposition, then you form that matrix,
Yes.
and that's the singular matrix. And I've done things like that to contrive some interesting examples. Well, actually, I can show you one of them. Okay. Okay. Oh, here it is. Okay. So, so here's a matrix, 2 by 2, and here are 2 right-hand sides. So, okay. Oh, it looks like I don't have numbers here. Okay, I'll just go ahead and type. Okay, I need to change my screen share here. Oh, I don't know before I should have done that. Oh, okay. So I go to MATLAB. Okay. Oh. Okay. So that matrix is okay, and the condition number of A. All right, it's not horribly conditioned, but it's not great either. So then, if I make right-hand side number 1 and right-hand side number 2. All two right-hand sides. So they're off by 1%. Evidently, I contrived it that way. But now if I solve the two systems of equations, these right-hand sides, there's x1 and x2. So they're a bit different. So if I look at that difference, yeah, so 1% change in the input, extremely, a much larger change in the output.
Yes.
Now, how I contrived that example, is that I made the small singular value particularly small. And if I look at the full singular value composition, look at the right-hand sides, these right here. So I used the first singular vector as one of the right-hand side, and then the perturbation of it in the direction of the other singular vector.
Yes.
And yes, it's contrived. The point is, if a matrix is terribly conditioned, something like this can happen. So we have to be wary of that. We still have some time. Other questions? Everything going swimmingly with homework? I know it's not due for another 5 days, so maybe some people haven't started it yet. I know how you all work. Or some cases don't work. There's nothing in the chat either. Okay, well I will stick around for anybody who does have a question.
Thank you, Dr. London.
Yep.
Thank you, Professor.
Yep.
Professor, can we prove that the condition number we use, you said that we use backwards relative error and condition number to compute or to estimate forwards relative number.
Yeah.
So can we prove that in the equation you said that it is backwards relative error times condition?
You can prove that the, for instance, the relative forward error
Yes.
is in magnitude is less than or equal to the condition number times the relative backward error.
Yes. So we can prove that
Yeah.
even if they use the matrix example. Yes, we
Well, I would say, in the matrix setting, you can.
Oh.
In general,
In
well,
general.
actually, well, it didn't hold in this case, but yeah, but it was a good estimate. But yes, it can be proven. Or actually, the proof I saw was it has like you make an order epsilon perturbation in the probable data, then you're neglecting terms of order epsilon squared. Although I think I might have seen a proof elsewhere that is more sound that actually shows it really is less than or
There's
equal.
no proof in the textbook. This in our textbook.
I'll just allow you to check the proof that I have.
Alright.
I think it did it a couple different ways, but
So is there any error bound for this equation? Means
well, yeah, there is. Well, Wilkinson did a very careful error analysis
Yes.
of actually mainly Roundup error, but backward error analysis of Gauss elimination. Okay, so in this case, oh, okay, yeah, okay.
What this is?
This factor here. So that's unfortunate. That's okay. If we're making an assumption, yeah. So you're solving a perturbed problem,
Yes.
or of some perturbation, but we're making this assumption about the size of the perturbation. So that has to be less than 1. And what that means is we have this factor. So if r is close to 1, then yeah, it's not just bounded by condition number times relative. This is a relative error in the input, relative backward error.
Yes.
That you have this fudge factor that can be large.
Oh.
Yeah. So now what that would mean is that if the perturbation is particularly small relative to a, then r will be small. So you could argue that in the limit, as the perturbation goes to 0,
Yes.
then this inequality without this
So you
factor,
bounded by the
Yeah.
right side.
yeah,
About the general case, it is about the matrix, right?
what?
The general case.
Oh, okay.
Or use maybe not involving any matrices.
Oh, okay. Yeah, but that, what I call it is Gauss elimination. The error can, you have some additional terms that actually can get quite large. So in fact, it depends on like the like for instance the pivoting strategy you used. That there's complete pivoting to prove that it's even stable. That's more of a stable algorithm as opposed
Yes,
to
the
conditioning.
algorithms.
Yeah. So I don't recall seeing like a proof about relationship between forward and backward error that doesn't make assumptions such as this. But it probably would get pretty ugly.
Yes.
Or have a very pessimistic bound.
Oh, another question is about last class you mentioned that you said that roots function is the inverse function of the poly function, right? We tried from 1 to 50.
Yeah.
And the result involves imaginary parts.
Yeah.
So how can that error be so large?
So
You mentioned that it's concerned about some eigenvalue problem?
yeah, it's not even like problem. So what happens is the so in this case, since the eigenvalues are supposed to be distinct, but eigenvalues have a condition number also. So if you have an eigenvalue that's distinct, so multiplicity 1,
Yes.
then the condition number is the inner product of its right eigenvector and its left eigenvector, assuming both are normalized. Or maybe one over that. But what happens is if the right and left eigenvectors are nearly orthogonal, yeah, it is 1 over the inner product. That the so the eigenvalue can be very badly conditioned. So it is possible, unfortunately, because we do have a very effective, efficient algorithm for computing eigenvalues, but they can fail. The problem is that the matrix involved is not symmetric.
Yes.
When it's symmetric, it's really nice, but so that's what happens in that case, and unfortunately, it's difficult to get around that. Well, and actually now I'm wondering if I look at companion matrix.
So maybe that use this mechanism to yes.
What?
Oh, MATLAB, so use the companion matrix
Yeah.
to
So if I get the polynomial
yes.
of matrix of that polynomial, and then get the eigenvalues and eigenvectors, then okay. If I look at the diagonal, okay, so okay, so I'll just pick an eigenvalue at random. So the right eigenvector would be I'll just pick like the fifth one, and then the left eigenvector. Okay, so I need to do okay, that's a problem right there, but
So it is
I need to get the left eigenvectors. Okay, so make sure it's normalized. So that's normalized. Okay. Oh, that's a problem. Okay, so all right. Well, okay, so condition number is 1 over yeah, that's an incredibly badly conditioned eigenvalue.
yes, yes.
So
So that's the reason why just if we involve, a large scale of the roots, and if we want to know what the original polynomial is, it involves so big conditional numbers. So it leads to so large error.
yeah, so now what you could try instead if you have that polynomial, well, what's probably happening if you look at the coefficients. Yeah, the coefficients are incredibly large.
Yes.
So, and since we can only represent so many decimal places accurately, these coefficients are horribly inaccurate. So even if you were trying a different method, for example, using Newton's method, then and then it converts to certain roots, when you divide the polynomial by that, the coefficients are still going to be inaccurate to start with. They won't get any better. So there's really nothing you can do.
So we can improve it.
No. That's what happens with the ill-conditioned problem. You need a different problem.
All right. So it is a kind of ill-post problem.
It is.
Oh, I see.
Yeah. So yes, it's a polynomial root finding. Well, when we get to chapter 10, I'm going to talk about root finding in general. That's I talk about how what's the condition number of that problem. And what happens is if a function is pretty steep at the root, then it's a well-conditioned problem. But if it's nice and flat, especially if it's a horizontal tangent at the root, then that's terribly ill-conditioned. So now in this case, we have distinct roots. So we're probably finding each individual root, but the thing is we have this source of error,
Yes.
so we can't even represent it. So,
Yeah, that's the reason.
yeah.
Okay, I see. All right. So, do you stop recording?
Oh, did I? Oh, okay. Oh, it's still recording.
Oh,
Okay.
all right.
Also, I'm not getting to these questions. So.